At the beginning of the 20th century, both theoretical and experimental scientists were grappling to understand how the universe works at very small scales. This gave birth to the field of quantum mechanics, which has led to innovations such as lasers and transistors that have substantially impacted our daily lives. This was the so-called first quantum revolution, which relied on the effect of quantum mechanics. But now in the 21st century, scientists around the world are trying to develop the next wave of innovation. The second quantum revolution relies on manipulating and reading out quantum states, and we typically exploit the quantum effect of superposition and entanglement. Few of the typical examples are quantum computing, quantum communications, and quantum sensing. To welcome the second quantum revolution, educating our younger generation on quantum physics becomes a key issue. Moreover, modern higher education of quantum physics is mainly implemented via pen and paper, namely the theoretical approach, making it quite opaque or less understandable. Therefore, a clearer understanding of quantum mechanics, especially some real hands-on experiments with proper demonstration kit, is highly desirable for university graduates who might enter this multi-million-dollar quantum industry. With a properly designed demo kit, students can easily gain an intuitive feeling of quantum physics by developing their own experimental protocols and performing quantum measurements independently themselves. The expected learning outcomes, including the basic understanding of rules in quantum mechanics, will effectively bridge core quantum concepts with emerging cutting-edge applications.
Hi, welcome to our lab. So we are here working with diamond materials, as shown here, like this one. So this is a piece of diamond, you see, and there are some kind of so-called color centers inside. It's kind of optical reactive defect centers, and we are actually relying on the spin properties, which we can make use of the so-called quantum behaviors, and we are performing the quantum sensing measurement here. So as shown here, this is a typical setup. You see this is a green laser, and then this green laser will shining on the previously introduced diamond samples, and then their emitted fluorescence is depending on their so-called spin states, the spin up or spin down, and the so-called quantum behaviors will make these spin defects a kind of quantum bits, right? They are either in the 1 state or in the 0 state, and this is the magic of the quantum world, and we are working on this quantum sensing, and we want to find the potential applications like the magnetic field sensing, like the temperature sensing, and so on and so forth. And one of the issues might be existing for education purpose is that you see here the setups. You see the typical setups relying on this spectroscopy based setup is too bulky, and it is not easy for us to take such a bulky setup to the classroom for demonstration. Therefore, we are looking forward to certain kind of, highly compact setup that is suitable for the education purpose. The nanoscale diamond particles, generally known as nanodiamonds, have several outstanding material quantities, offering a broad range of potential applications ranging from the basic science to the industry. Now you can take a look on the sample I shown that those gray powders in the tube is the nanodiamonds. This gray color is actually coming from the associated impurities such as the non-diamond structures, those disordered carbons introduced during their synthesis processes. Those impurities are the unwanted parts will significantly limit the widespread usage of the nanodiamonds. Therefore, purification of the nanodiamonds is a primary step to realize most of the practical applications. Unfortunately, it is difficult to eliminate those unwanted parts using any existing methods like the conventional air oxidation approach. In this invention, we developed a simple, reliable, and reproducible purification method, namely the salt-assisted air oxidation SAAO method. It requires only one additional pre-step, that is, mixing the nanodiamonds with the proper amount of salt crystal, the sodium chloride, prior to conventional oxidation. So you can see in this tube with the gray color, this is a mixture of the raw nanodiamonds and the sodium chloride powders. And the other tube with the white color is a mixture after the oxidation, the clean nanodiamonds now inside. Our method runs original sharp-like shape of the nanodiamonds with a clean surface and can be scaled up to permit their manufacture in large quantities but with low cost. This important breakthrough will significantly enhance the scope of those little gemstones in diverse scientific and industry fields, particularly in demanding areas such as biomedical applications requiring stable and sound surface functionalities. the point defects that in the diamond nanomaterials, like the nanodiamonds, is very useful, has been a huge potential in diverse fields. However, due to the limited sensing volume of these emitters, it becomes necessary and very important to accurately position them with targets on any of the useful substrates. Up to now, rare schemes of positioning single diamond defects that we have developed this so-called on-demand printing of the quantum nanodiamonds directly on any of the substrates without any limitation. You can see here that these nanodiamond particles can be positioned with a high precision down to the diffraction limited spots listing as shown here, and this is one of the typical examples. You can see a single defect has been identified. And this is just one of the technology. Another technology we have been developing recently, a lithography-based, low-cost, scalable method that can be used to pattern the nanodiamonds at the wafer scale level. This is ongoing research, and we expect this will help us a lot.